Our next video is about the other kind of improper integral. We already talked about the first one, a definite integral with an infinite limit of integration. The other type of improper integral is a definite integral of an integrand with a finite number of discontinuities. So what we're talking about with these discontinuities generally are vertical asymptotes. If we look at this definite integral, this, by the way, is the definite integral of 1 over x squared. We can see that 1 over x squared, when x equals 0, has a vertical asymptote, which means that at this spot right here, I have a slight problem in that the area keeps going up, and that's going to happen forever. When that's the case, we're going to use pretty much the same idea as we did last time of how we find or attempt to find the definite integral, and that's by turning to limits. The difference is that if we're dealing with an improper integral because of a discontinuity, what we're going to need to do is chop that integral up into two parts. The part before the discontinuity and the part after the discontinuity, and we add them together. So if you're dealing with a definite integral of a function that has a discontinuity somewhere in between the limits of integration, you're going to chop it up into two different limits of integrals. So let's see how that works in an example. We'll try this one. The definite integral from negative 3 to 3 of 1 over x squared dx, and that's like the graph we were looking at on Desmos a second ago. We know 1 over x squared has a discontinuity, a vertical asymptote at x equals 0. So what we need to do is chop this one up into two pieces. First, we'll take the limit of the left-hand side, so that's the definite integral from negative 3 to b. I'm using a b there because it's the upper limit of integration of the left-hand side. As b approaches that discontinuity, which we know is 0, but what's important here is we have to remember we're talking about approaching it from the left. And we have to add that to the other side of the definite integral from negative 3 to 3, which would be the limit from a to 3, so that's the right-hand side of 1 over x squared dx, evaluated from, as b approaches 0 from the right-hand side. So we've chopped up our definite integral into the limits, two different limits of different integrals, definite integrals, and we're going to have to do them one at a time. So for both of these, we're going to use the same antiderivative, so that's at least convenient. We'll have the limit as b approaches 0 from the left of the definite integral from negative 3 to b of 1 over x squared would evaluate as the antiderivative of 1 over x squared evaluated from negative 3 to b. And it's going to look very similar on the right-hand side. It'll be the limit as a approaches 0. I just noticed I put a b here when I meant to put an a. From the right of we'll evaluate the definite integral here, which is, again, the antiderivative of 1 over x squared evaluated from a to 3. And we're still going to just keep chopping this up one piece at a time. So it's still the limit as b approaches 0 from the left, and we'll evaluate negative 1 over x from negative 3 to b. Put that in brackets so it's easy to separate. That's negative 1 over b minus negative 1 over negative 3. That's the left-hand side. And on the right-hand side, it's the limit as a approaches 0 from the right of negative 1 over 3 minus negative 1 over a. And it's possible that you already see the problem we're going to run into here. The limit as b approaches 0 of 1/3, that's easy. But the limit as b approaches 0 of negative 1 over b, doesn't exist. Sure, this is going to be plus 1/3. And on the other hand, I can evaluate the limit as a approaches 0 of negative 1/3 is, of course, just negative 1/3. But again, my similar problem here, the limit as the denominator approaches 0, neither of those two limits that we're left with exist. In any point we have a limit within a problem that doesn't exist, our whole integral diverges. And around this vertical asymptote, we cannot find the definite integral. It doesn't exist. It's infinitely big. But do note, that's not always the case. Just because there is a vertical asymptote does not mean that there is no definite integral. So let's take a look at the graph of what I have here. It's the definite integral from 0 to 1. So I'm going to first put that in there. And it was the graph of the cube root of x. So we are looking for this. And notice again, there is a vertical asymptote here. I do have an infinite amount of space up here, or at least an infinitely high amount of space here. But let's see if we can measure this definite integral anyway. And this is one of those cases where it just turns out to be a little bit surprising what we can turn up with in the end. So the definite integral from 0 to 1 of 1 over the cube root of x dx. Again, because it's an improper integral, because of the discontinuity at x equals 0, we need to turn it into a limit. The limit of our definite integral, I'm going to change the lower limit to an a because it can't be 0 because 1 over the cube root of x doesn't exist there. And just to make it easier to do the antiderivative in just a second, I'll write that as an exponent, as a power, as our lower limit approaches 0 from the right. And now I can evaluate that definite integral inside the limit. The definite integral from a to 1 of x to the negative 1/3 is the antiderivative of x to the negative 1/3, which is x to the 2/3 over 2/3, evaluated from a to 1. And let me do that evaluating from a to 1 while it's still inside the limit. So that's 3 times 1 to the 2/3 over 2. Well, that's just 3/2. Minus 3 times a to the 2/3 over 2. And it's the limit of all of that as a approaches 0, which would be 3/2 minus the limit of 3a to the 2/3 over 2 as a approaches 0. But with this limit, I could just do direct substitution right now. I can plug a 0 in there. So that equals 3/2 minus 0, which is just 3/2. So even though there is a vertical asymptote in this graph, this definite integral actually is 3/2, no matter what. And one thing I can do here is I could try that. I can find the definite integral. I'll start with 0.1 to 1 of x. I'll write out the way we saw it before, nth root of the cube root of x. And what I can do is show you that as that lower limit of integration gets closer and closer and closer to 0, my definite integral is getting closer and closer and closer to 3/4, which is not what I thought it was going to be, but that's something I can figure out later. The key is, I'll have to go back and look and see what I did wrong, but the key is that this limit, this definite integral does seem to exist, even as my lower limit of integration gets infinitely close to 0, the definite integral still seems to exist at 3/4. I did just take a quick look at what I had done, and I realized I had just simply mistyped the integral into Desmos. I had written the cube root of x, not 1 over the cube root of x. And so I corrected it in Desmos, and now you can see that as my lower limit of integration gets infinitely small, my integral is approaching 1.5. See how far I have to go before it rounds to 1.5. I guess I can't even handle these numbers. But you can see that it is not getting bigger and bigger and bigger. It is 1.5.